Welcome to acoustical test of hearing protectors. My name is Ole Teilgaard. I'm director for global support. Global support takes care of the brand Audio Precision and the brand Grass Sound and Vibration. Both of these brands are a part of the Axometrics Solutions Group. Let's start with the agenda. As I mentioned before, today's agenda is acoustical test of hearing protectors. So what are we going to look at? First, we will start with a little introduction. In this introduction, we will have a short talk about noise and sound. We will have a talk about maximum daily noise dose. And we will also have a look at the different types of hearing protectors. Next, we will look at the different standards involved with test of hearing protectors. And then we will have a look at test and measurement requirement for doing test, verification, type approval test, and things like that of hearing protectors. We will look at the challenges by carrying out these tests and verifications. We will look at solutions, equipment to use. Then we will have a look at test of the different types of hearing protectors. And in the end, there will be some time for questions. I have to mention concerning questions that please use the Q&A function in this webinar and place your question there. You can place the questions during my presentation, but I will only answer after the presentation. So right after the presentation, then I will try to do my very best to answer all the questions there might be in the Q&A function. Okay, sound and noise. Yeah, when we are talking about sound and noise, then we are talking about what the human being actually can hear, what we can hear as human. We can hear very, very low signals in both frequencies and in levels, low sound pressure levels, low frequencies. We can also hear higher frequencies, also very high frequencies, up to 20 kilohertz as a human. And we can also hear very, very loud signals, very, very loud sound pressure levels. So what is sound? Yeah, sound is actually energy transmitted by pressure waves in air or any other media, and is the objective cause of the sensation of hearing. We can also say that sound can be described as any pressure variation. It could be in air, water, or in any other medium that the human ear can detect. And then, yeah, sound, it can actually be wanted if we listen to music. It can also be unwanted if we don't like that kind of music. It can be very, very pleasant and it can also be very, very unpleasant. The unwanted, the unpleasant, or very loud sounds is also defined as noise. If we look at maximum daily noise dose, it is so if we as a human is in an environment with very loud sound or very loud noise, then this very loud noise sound will actually damage the cells and the membranes in our ear. If we are listening to loud music, loud sound, loud noise for a long period of time, then it will actually overwork the hair cells in our ear, and it will cause that these cells will die. The hearing loss progressiveness will be as long as we are exposed for a very high sound pressure level. Harmful effect might also continue even after the exposure has stopped. So, to protect us human against hearing loss or damage, then we actually have a standard for the maximum allowed noise we can be exposed for during a 8-hour working days. This noise dose is normally defined as 100% within these 8 hours working days. It is a maximum sound level, and it is actually the maximum sound level you can be exposed for during a day. This sound pressure level might differ from country to country, but most of the country all over the world, they are actually using 85 dBA as maximum sound pressure level we can be exposed for during maximum 8 hours. If we increase this sound pressure level, then we are only allowed to be exposed for that very high sound pressure level in a shorter period of time. For instance, if we increase the sound pressure level to 88 dB by 3%, a doubling of the power of the effect, then we can maximum be in that environment for 4 hours. And if we add again 3 dB to the sound, then we will halve the hours we can expose for that high sound. So 91 dB is equal to 2 hours, 94 dB is equal to 1 hour, and so on. Hearing protectors. Yeah, the hearing protectors or ear protections are devices used to protect the human ear or hearing against hearing damage. People, workers, should actually wear hearing protectors if the noise or sound level in the environment, in the workplace, exceed 85 dB. Hearing protectors reduce the noise exposure level and the risk for hearing loss. We have different types of hearing protectors. We have what we call earplugs. It's an soft foam which is stored inside the ear canal. We have ear muff, which is externally like a headphone, which is placed around our externally part of the ear. We could have helmets with ear muff, so we have protection of our hearing, but also protection of our head and so on. Noise ratings serve as a standard way to measure and specify noise in buildings and working places, etc. The noise rating is a single figure rating system which also takes into account the frequency contents of the noise signal. In a very, very simple example here, we could have in the environment around us 120 dBA. And as we learned before from the previous slides, then we are only allowed to be exposed for 85 dBA during a working day. So in this case, we have actually to reduce the noise level, and it's will of course be reduced by the hearing protectors. But there are some requirements to the hearing protectors. In this case, they should actually reduce the noise with 35 dBA. And for this, we are actually using the noise rating curves, because the noise rating curves will actually look at the highest noise level in frequency and then give us a number for how good these hearing protectors must be to be able to have the correct damping of the noise. Standards. When we are talking about all types of measurements, all types of tests, then we need to have a look at the different standards involved with test of the device we would like to test. And for hearing protectors, one of the standards we have to have a look at is the EN 352 standard. This standard describes the general requirements for an hearing protectors. It's a general requirement for both ear muff, ear plugs, and all types of hearing protectors. So this is more a general requirement. The EN 13819 describes the test methods we have to carry out when we are doing test of hearing protectors. So they describe both the physical test we have to do. They do also describe the acoustical test methods, and that's actually what we are concentrating on today, the acoustical test of the hearing protectors. We also have to have a look at the ISO 4869 standard. This standard describes the requirement for the test. It's described how to carry out the test, while the EN 13819 just tells us that we have to carry out a test, and the test methods we have to use is actually described in ISO 4869. The ISO 4869 consists of, like all the other standards, of different parts. and different way of doing test. What we are most interested in is actually the ISO 4869-3, which is the acoustical test of hearing protectors. We also have to mention the ANSI standard S1242. This is a method of measurement in certain laws of hearing protectors devices with continuous noise or impulse noise. And these protectors, according to the ANSI standard, are protectors mainly made for impulse noise protections and measurements. If we look at a typical measurement setup when we are talking about the acoustical test of hearing protectors, then a typical measurement setup will consist of a test fixture. It could be ear simulators and of course microphones for picking up the noise. Sound source, we need to have a sound field generated around our test fixture. A sound field which is more or less equal to what we expect in the environment in which we would like to use our hearing protectors. We will have a reference microphone placed in the environment around the test fixture, because of course we need to know the sound pressure level generated by our sound source. We need an audio analyzer able to generate a signal we can apply to our sound source, and it also needs to have an analyzer section so we can measure the response both for our reference microphone as well as for the microphone placed in our test fixture. We need a power amplifier for driving our sound source, the loudspeaker we can see here. This test equipment, this test setup, should actually be placed in a test room, of course, and this test room should have reverberation function. It should be a hard room with a good reverberation function to be able to build up a homogeneous sound field. We will come back to this homogeneous sound field in one of the next slides. If we look at the procedure, what we actually have to carry out according to ISO 4869-3, then first of all we have to prepare the room for doing the measurements. So the first thing we actually have to do is actually removing our fixture from the room. So don't start installing the fixture, because the first thing you have to do is actually removing your test fixture from the room. So we have to have our sound source, our speakers, and normally we will place the test fixture in the middle of these speakers, but we actually have to start removing the test fixture, so we will start with that. And now we have to set up the sound field according to the below specifications. First of all, we have to adjust the sound field, and this is actually done by measuring the noise in 6 positions. In 6 positions, it means that we will actually start measuring the noise with our reference microphone in the same height as the top of the test fixture, the same height as the test fixture. And then we will lower the microphone, so the microphone is in same height as the ear entrance of our test fixture. And then we actually have to measure in 4 positions. So the first position where we start measuring is a reference position, and then we measure in 4 positions. And then the last measurement we are doing is actually a general measurement, but measure in the lower part of the fixture, where the fixture actually would be. When we have done these 6 measurements, then we will look at the max deviation between these 6 measurements. The max deviation from our reference point, the first measurement we did, is 2.5 dB. And then we also have to ensure that the difference between left and right is less than 3 dB. When we have adjusted our field according to these specifications, then we can actually start doing our measurement. So the first thing we actually will do, we will actually place the fixture in our sound field. We will place the fixture without any hearing protectors. And then we will start doing a measurement. And the measurements we have to do is at least a 1 octave measurement together with an A-weighted measurement and together with a C-weighted measurement. And we have to average over at least 30 seconds. When we have done this measurement and we have stored the results from these measurements, then we have to mount the hearing protectors on the fixture. It's done now, and then we have to do an additional measurement, and the additional measurement is actually the same type of measurements as we did before, but this time with the hearing protectors mounted. And again, we do it in 1/3, in 1 octave measurements, A-weighted and C-weighted, and again with an averaging time of at least 30 seconds. And then we have to, when we have done the measurements, and then we can actually calculate the attenuations of the hearing protectors and find the hearing protector or the protection level of that pair of hearing protectors. If we look at the level and signal, then the signal, the generated signal we apply to our sound source, it should be a pink noise signal or an equivalent or another type of a noise signal. The level to the sound source is actually interesting, because when we talk about the level to the sound source actually should generate, then there are some parameters that have an influence on that. And one of the parameters is the fixture we are using, the self-inserting loss, the SIL of the fixture we are using. The self-inserting loss for test fixtures, according to the standards we mentioned before, are actually always specified. And then we have to look at the microphone we are using internally in the fixture, we have to look at the self noise of this microphone, self noise or the inherent noise, the lower limit of dynamic range of this microphone we have inside the test fixture. And this is also a parameter which is specified for all types of microphones. So it's actually something which is easy to get. And then when we are doing measurements like this, then we have to ensure that we have at least 10 dB signal to noise ratio between our microphone and the test we would like to perform. And then we can actually use this formula. We have to, that the sound source level, it must be higher than the damping of the fixture, plus the microphone self noise, plus the signal to noise ratio, the headroom. And if we use the example we have here, then the SIL for test fixture is about 65 dB. The lower dynamic range of a microphone is 14 dB. We have 10 dB signal to noise headroom. So our sound source level should at least be 89 dB. When we are doing measurements like this, then or test of hearing protectors, then typical levels, test levels is between 100 and 120 dB. So the acoustical isolation or self-inserting loss of the test fixtures must actually be as high as possible, because otherwise we are actually not measuring on our hearing protectors, but more testing our test fixtures itself. And that's actually not the idea. And then according to the standard, then the test fixtures should actually be mounted with either a 1-inch pressure microphone or a 1/2-inch pressure microphone according to the standard. For doing tests of earplugs where you use the ear canal, then you need actually an ear canal. So you will need what we call an ear simulator, an IEC 6318-4 ear simulator. I will also come back to that in a few slides. Measurement, the measurement challenges. Requirement for doing the measurement is a 2-channel analyzer. We have 2 ears we would like to measure at the same time, so therefore we need at least 2 times. Minimum 1 octave. We need also A rating, we need C rating, and we should be able to do everything for minimum 30 seconds. Data, and then we need to do some calculations with the data we have measured. We need to do calculations. First of all, we need to do measurements and calculations without the hearing protectors. Then we have to do the measurements with hearing protectors, and then we do the calculations where we actually are finding the difference between with hearing protectors and without hearing protectors, which give us actually the noise attenuation for the hearing protector itself. If we look at noise reduction systems, because there are actually different ways of doing the calculations. What we saw in the previous slides were a very, very easy way of doing it. Most of the way of doing these calculations are a bit more complicated. We will have a little look, not going to all these calculations in details. But what do we actually have? We have what we call SNR, single number rating, which is a system used in Europe to indicate the amount of protection offered by a correctly fitted hearing protector. The SNR give us an overall rating. The system will also rate the protectors in terms of particular noise environment in which they will be used. It means it will actually tell us about the protector's high frequency performance by telling us the damping in the high frequency environment, in the mid frequency environment, as well as in the low frequency environment. Then we have another noise reduction system. It's the noise NRR, noise reduction rating. This is a rating system used in the US. The system we are using today is giving us a number between 0 up to 33, and this number is in decibel, tells us about the noise reduction of the hearing protectors. And it will describe how much the all-over noise level is reduced by the hearing protector. So when we are doing calculations and finding the effectiveness of the hearing protectors, then there are actually 4 methods for doing these calculations. We can do a calculations called the octave band methods, where we actually do the calculations directly by our measurements in octave bands. There are also another way of doing it is high, medium, and low in frequency, where we actually require our measurements of our C-weighted measurements and our A-weighted measurements for doing the calculations of the different attenuations. The HML control is a simplified version of the HML methods. This method requires only the measurements in dBA. And then we have the SNR methods, which requires one attenuation value. And this is actually subtracted from the C weighting sound pressure level that is measured. So if we have a closer look, the octave band measurement, for doing the octave band method, then it's required that we have measured the damping of our hearing protectors in octave bands, and it also require that we do an A-weighted measurement, and then we start doing the calculation of the measurement, where we actually are using our measure results and make an average of these measurement results. In principle, it is actually what we have measured without hearing protectors, and then we actually subtract what we have measured in the different octave bands, the sum of the different octave bands. So we end up with the final result in this case where we have 23 dB. In practical, it is more difficult when we are using the formula. The HML methods, it require an A-weighted and a C-weighted measurement. The calculations of the and then we had to calculate the high frequency attenuation, the mid frequency attenuation, and the low frequency attenuation. And it is normally or mainly based on 8 reference noise spectra, each with the difference between the C-weighted and the A-weighted values, and the individual sound of the hearing protector's attenuation value is then calculated. The SNR methods, it required a C-weighting measurement and must be based on a pink noise excitation signal. Basically, the SNR signal is actually the C-weighted minus the A-weighted, but in practical, the calculations is actually much more complex. If we look at the type of measurement equipment we have to use when we are doing these measurements, then a fixture like the GRASS 45CA headphone and hearing protector test fixtures can actually be used. If we look at the specifications for this fixture, then we have a self-inserting loss SIL in the frequency range from 80 Hz to 20 kHz of minimum 50 dB. We have a dynamic range for the microphone installed inside from 27 dBA to 164 dB. If we use a 1-inch microphone inside, then it's 14 dBA to 146 dB. And we are following the ISO 4869-3 standard. If we would like to test earplugs, here ear protectors we place inside the ear canal, then we need a human-like ear canal where we can place our earplug, and we need an ear simulator to pick up the noise inside the ear canal or after our hearing protector. For doing this, then we need actually an ear simulator, and we need what we call a pinner with an ear canal. If we look at what we actually can test with the different version of the 45CA, then let's have a look. There's a 45CA-1 and -2 is actually where we have either a 1-inch microphone or a half-inch microphone, and with these we can actually test earmuff and we can test helmets. In the 45CA-7, it's where we have the ear simulator. It's the one we can use for testing earplugs. Yeah, they can actually be used for earplugs. They can also be used for earmuff and helmet, and yeah, variation of these. Another test fixture, the 45CB-S1. The 45CB is actually a test fixture made according to the ANSI S12, that's 42, and this S1 is a high sensitive version. Specification, minimum 60 dB in certain laws. We have a measurement range from 27 dB up to a very high level, 164, and we are, of course, according to this ANSI standard. Special with this one here is that the ear canal is actually heated up to body temperature, 37 degrees. So we have, if we look at it, we have the heating element. So the ear canal, we can see here, the ear canal is actually the one with the orange color here. The ear canal has a length in this on 14 millimeter according to the ANSI standard. And with this, we can actually test all types of hearing protectors, ear plugs, ear muff, helms, and variation of these. Reference microphone. The reference microphone, it could either be a free-fill microphone like the Grass 46AE microphone. This is a microphone, a free-fill microphone following the standard for free-fill microphones and measurement microphones, or it could be a quarter-inch microphone, quarter-inch free-fill microphone. Again, it will actually follow also the standard, or it could be what we call a random incident microphone. A random incident microphone is actually perfect to do the measurement in an reverberation room, in a reverberation environment, because the random incidence microphone will actually is not depending on the direction of the microphone. It will actually measure the sound pressure level from all directions, where the standard free-fill microphone is sensitive in one direction. You have actually to point at the sound source with that microphone. But the fields here, but a standard free-fill microphone, you can actually convert it into a random incident microphone by adding a little adapter in front of the microphone, a little random incidence adapter. If we look at the requirements for the analyzer, then we need to have a 2-channel analyzer. It has to be able to measure octave. It has to be able to measure A rating, C rating, and averaging. The averaging time should be at least 30 seconds. We need also a generator, and it could either be that should be a pink noise generator. It could also be that the analyzer supports wave files, so we could make a noise file ourselves according to our own specifications. We need an power amplifier, and the power amplifier should of course be powerful enough to drive the necessary amount of speakers. A good example for an analyzer which actually will fulfill many of the requirements here is our APX 517, the B-series acoustical analyzer. This analyzer has a built-in 35 watt power amplifier. It has also inputs for our microphones in the test fixture and our reference microphones, and can be supplied with the necessary software for being able to carry out the measurements, or carry out to get the data for the measurements. The analyzer itself does not have built-in calculators for the different test methods we talked about before. If we look at test sorry. If we look at test of passive ear protectors, in-ear, ear muff, and helmets, then we have to measure the sound attenuation according to the standard. The test setup we have to use is the standard test setup based on an ISO 4869 fixture or an ANSI S12-42. It is actually the test fix setup we start looking at in the beginning of this webinar, consisting of the test fixture mounted with microphones or ear stimulators, speakers for generating the sound field, a homogeneous sound field around the fixture, a reference microphone for measuring the sound field, the level in the sound field, and then the analyzer for picking up and generating the signal to the sound field. Active protectors. See that we do also have active hearing protectors. Active hearing protectors where we have a noise reduction or a level depending protectors. Again, we have to measure the sound attenuation according to the EN 13819, that's 2 standard. And again, we have to use the same setup as we had before, and we have to do this has to be done in 2 steps. We have to first of all make a measurement of the active noise reduction, where we have both the passive and active part measured, and then we have to for level depending protectors, we have to do a measurement of the passive reduction and for the level depending reduction. There are also protectors available on the market with radio built in, Bluetooth communication and Bluetooth connections built in. Again, for the hearing protection part, we have to do the measurements according to the EN 13819, that's 2. The setup is the same as we saw on the 2 previous test setup. And then, of course, we also need to do a test of our radio or Bluetooth communication. And yeah, it is actually a test of the standard sound quality parameters. And for doing these tests, we can actually use the standard IEC 60268-1 test signal. This is a test signal simulating the shape in frequency of a long speech or music signal. And if we continue with this test of the sound quality, its parameter we have to measure, like frequency response, we have to measure level, we have to measure sensitivity, we have to measure max level in the protectors coming from our radio or Bluetooth or the communication. We have to measure a crosstalk between the 2 channels, and then if there are a communication microphone, then we have to measure frequency response of this, sensitivity level of this microphone, phase of this microphone, might be directivity. And again, when doing test of the communication microphone, then the IEC 60268-1 text signal could be a very, very good idea to use for doing these tests of the microphone itself. If we make a conclusions for what we actually have been looking at today, then we need to use a test fixture with a high SIL, self-inserting loss. The test fixture has to be in accordance to the ISO 4869-3 or according to ANSI S12-42. The measurement we have to do, we have to carry out measurements in A rating, C rating, octave, at least 1 octave, but 1/3 octave will probably give us a much better picture. The test signal, it should be a pink noise signal, and the test signal should be as high as possible and minimum equal to the self-inserting loss of our test fixture, the inherent noise of the microphone we are using inside the test fixture, plus a signal to noise margin, normally about 10 dB. And it should actually be a homogeneous field we are using. If we remember from one of the first slides, when we were looking at the field, then we actually had to measure this the homogeneous field in 6 positions, in the microphone in 6 positions, and the deviation between these different positions should be less than ±2.5 dB, and the maximum difference between left and right is less than 3 dB. For sound quality test of a communication microphone, we will recommend that we actually use an IEC 60268-1 test signal. Questions: how to make the calculations? How to make the calculations. Many of these calculations, normally when you have done the measurements, then you will actually export your measured data to a computer, and on the computer you could actually have an Excel spreadsheet, and then you can actually do the calculation in Excel. You can also export your measured data to a MATLAB program and do the calculations in a MATLAB program. Many of the analyzers are not dedicated for measurement hearing protectors, so they do not have these calculations directly in the software, but of course it is possible to do it in the analyzer if you had the software directly in the analyzer. There's one asking if the famous one of the other analyzers in the axiometric solutions group, or manufacturer in the axiometric solution group, IMC, they produce an analyzer series and software series called Famous. And yes, you can also use Famous for doing the measurements, and I'm not sure what you can actually do of calculations in Famos, but it might be possible also to do a part of it, or export the data obtained in Famos to an Excel or MATLAB or an other externally calculated program.